Information theory. Information theory is the invisible force that shapes the modern world, yet its principles are often misunderstood or overlooked. At its core, it is the study of how information is measured, transmitted, and understood in a universe governed by entropy and complexity. While it may seem abstract, information theory underpins everything from the internet and telecommunications to biology and quantum physics. To grasp its significance is to gain insight into the fundamental fabric of reality. Imagine you're playing a game of 20 questions. The objective is simple. Someone thinks of an object, and you try to figure out what it is by asking yes or no questions. Each question you ask eliminates possibilities, narrowing down the range of potential answers. The fewer questions you need, the more efficiently you're gathering information. This game, in essence, illustrates the principles of information theory, the quantification of uncertainty, and the transmission of meaningful data. In the mid-20th century, Claude Shannon, often referred to as the father of information theory, formalized these ideas. Working at Bell Labs, Shannon was tasked with improving communication systems such as telephone lines. He realized that the fundamental challenge was not just noise on the line, but the inherent uncertainty in transmitting a message. Shannon's groundbreaking 1948 paper, A Mathematical Theory of Communication, introduced the concept of information entropy, a measure of the unpredictability or randomness of a message. The higher the entropy, the more uncertain or complex the information. To illustrate, consider flipping a coin. A fair coin has two possible outcomes, heads or tails, with equal probability. Each flip carries one bit of information, a term Shannon coined. A bit is the smallest unit of information, representing a choice between two equally likely outcomes. Now imagine a biased coin that lands on heads 90% of the time. Because the outcome is more predictable, each flip carries less information. This principle explains why a text filled with random letters has more entropy and requires more bits to encode than a coherent sentence in English. Information theory goes beyond simple coin flips. It addresses the efficiency of encoding messages and the limits of transmitting them through noisy channels. A key insight from Shannon's work is that every communication system has a maximum rate of reliable transmission, known as the channel capacity. For instance, if you're trying to send a message over a crackly phone line, the channel's capacity determines how much of the message can get through without error. Shannon demonstrated that it's possible to approach this capacity by encoding the message in a way that compensates for noise, a principle that laid the groundwork for error-correcting codes used in everything from CDs to satellite communications. The beauty of information theory lies in its universality. It applies not only to human-made systems, but also to natural processes. In biology, for example, DNA can be thought of as a communication channel where genetic information is encoded, transmitted, and decoded. The double helix carries instructions for building proteins, and its structure is remarkably efficient at storing and replicating information. Mutations, akin to noise in a communication channel, introduce variations that drive evolution. Information theory helps biologists quantify the complexity and fidelity of these genetic messages, offering insights into everything from heredity to disease. In neuroscience, information theory sheds light on how the brain processes sensory input. Your eyes, ears, and skin constantly receive signals from the environment, light, sound, touch, and your brain must filter, encode, and interpret this barrage of information. The retina, for example, acts as a data compressor, reducing the vast amount of visual input into a manageable stream of signals sent to the brain. This process mirrors the compression algorithms used in digital images and videos, where redundant or less significant data is discarded to save space. Perhaps one of the most intriguing applications of information theory is in understanding the nature of reality itself. Theoretical physicists have begun to explore the idea that the universe operates like a giant informational system, where physical laws are akin to codes and spacetime is a medium for transmitting data. This perspective is especially prominent in quantum mechanics, where the concept of quantum information challenges traditional notions of locality and causality. Quantum entanglement, for instance, can be seen as a form of information transfer that defies classical constraints, linking particles across vast distances instantaneously. Yet, information theory also highlights the limits of knowledge, the uncertainty principle in quantum mechanics, which states that certain pairs of properties, like position and momentum, cannot be precisely measured simultaneously, can be reinterpreted through the lens of information. It reveals that there is a fundamental trade-off between the information we can gather about one property and another. Similarly, in classical systems, chaos theory shows how small uncertainties in initial conditions can grow exponentially, making long-term predictions impossible despite deterministic laws. Another fascinating implication of information theory is its relationship with entropy in thermodynamics. At first glance, thermodynamic entropy and information entropy might seem unrelated. The former describes the disorder of physical systems, while the latter quantifies uncertainty in messages. However, they are deeply interconnected. In the 19th century, physicist Ludwig Boltzmann showed that entropy is linked to the number of microscopic configurations that correspond to a macroscopic state. Shannon's work extended this idea to the realm of information, showing that entropy is a measure of missing information about a system state. This connection has profound implications for understanding the flow of time, as the increase in entropy aligns with the arrow of time we experience. In the digital age, information theory underpins technologies that have transformed society. The Internet, for example, relies on protocols that encode, transmit, and decode vast amounts of data efficiently. Video streaming platforms, online communication, and even artificial intelligence owe their existence to principles first articulated by Shannon. Compression algorithms, such as those used in JPEG images or MP3 audio files, reduce file sizes without sacrificing quality by eliminating redundant data. These algorithms embody the trade-offs and efficiencies at the heart of information theory. Despite its ubiquity, information theory is still evolving. Researchers are exploring its applications in emerging fields like quantum computing, where information is encoded in quantum bits, or qubits, that can exist in superpositions of states. Unlike classical bits, which are either 0 or 1, qubits can represent multiple possibilities simultaneously, enabling unprecedented computational power. However, quantum systems are also highly susceptible to noise, and understanding how to correct errors in these systems requires a deep understanding of both classical and quantum information theory. As we continue to uncover the secrets of information, one thing becomes clear. Information is not just a tool for understanding communication systems or building technology. It is a fundamental aspect of the universe, a thread that weaves together physics, biology, and human experience. From the codes in our DNA to the algorithms that guide spacecraft to distant planets, information shapes our reality in ways both profound and subtle. Information theory teaches us that at the heart of complexity lies a simple, elegant truth. The universe is a conversation, and we are part of the dialogue. Hawking radiation. One of the deepest and most contradictory outcomes in today's physics gives us insight into the unusual conduct of black holes and their link to the quantum realm. At first, the suggestion that black holes, entities known for capturing everything, even light, might emit radiation appears to defy logic. Nevertheless, this concept has become a fundamental element in theoretical physics, demonstrating the deep connections among quantum mechanics, general relativity, and the universe's underlying nature. In 1974, British theoretical physicist Stephen Hawking introduced the notion that black holes aren't entirely devoid of emissions. Rather, they release radiation owing to quantum-level phenomena occurring near the event horizon, the dividing line beyond which nothing can return. This emission, termed Hawking radiation, results from the strange particle dynamics found in the vacuum of spacetime at the edge of a black hole. To comprehend Hawking radiation, begin with a core quantum mechanics principle, the nature of vacuum. In classical terms, a vacuum signifies empty space without matter or energy, but quantum theory views it differently. The vacuum is filled with momentary particles that briefly appear and then destroy each other almost instantly. These temporary virtual particles exist due to the uncertainty principle, which allows brief energy disturbances in what we see as emptiness. Now place this phenomenon at a black hole's event horizon, the threshold past which light cannot return. Quantum field theory tells us that virtual particle pairs, one with positive and one with negative energy, continually emerge and vanish. Yet near the event horizon, something remarkable may occur. The powerful gravity can separate these pairs before they recombine. One gets drawn into the black hole, the other escapes. To an outside observer, it seems as if the black hole is releasing particles. The one escaping, with positive energy, flies outward. The one consumed, with negative energy, lessens the black hole's total mass. This describes Hawking radiation, black holes discharging particles thanks to quantum phenomena at their event boundary. Hawking's revolutionary realization introduced the possibility that black holes gradually shed mass. As they emit this radiation, they slowly shrink. If this emission goes on indefinitely, a black hole could eventually lose enough matter to vanish altogether, leaving just the radiation. This idea of black hole evaporation redefines the traditional assumption that black holes are eternal cosmic features, offering a novel interpretation of their fate. To better understand this, consider energy conservation. Typically, when virtual particles form and disappear, one has positive energy and the other negative. They cancel out, causing no net energy change. But when one falls inside a black hole, it contributes negative energy to the black hole, reducing its mass. The other, escaping with positive energy, appears as radiation. This leads to mass loss over time. The heart of the black hole evaporation theory, the concept that black holes might contract and dissolve via Hawking radiation, has wide-reaching implications. It suggests that black holes, once thought to persist forever, may all eventually disappear, their legacy marked only by faint radiation. Still, Hawking radiation remains a theoretical construct. It hasn't yet been directly measured. The reason? This radiation is extremely weak and subtle, especially from larger black holes. A stellar mass black hole's radiation would be so dim that today's instruments likely couldn't detect it. Conversely, very small primordial black holes, which would radiate much more intensely, might already have vanished, making detection equally unfeasible. Yet, even without direct observation, Hawking radiation plays a crucial role in our understanding of information and core physical laws. A central mystery tied to it is the black hole information paradox, a conundrum that has puzzled scientists for years. Quantum mechanics insists that information about a system's state can never disappear. But if a black hole evaporates entirely, what becomes of all the data it swallowed? Hawking radiation complicates this. It seems to be random, without any imprint of what entered the black hole. This implies a potential breach of information conservation, a basic rule in quantum theory. Some theorists think the answer to this lies within the radiation itself. One explanation suggests the data from objects that fall into a black hole might not be destroyed but instead hidden, deeply encoded in the outgoing radiation in a disordered way. This theory, sometimes called soft hair, proposes black holes possess more information than once believed. That information could be buried within the Hawking radiation's subtle patterns. If this proves correct, it could solve the information paradox and provide profound insight into the link between quantum theory and gravity. Studying Hawking radiation also helps us better grasp the underlying design of spacetime and the puzzle of quantum gravity. The gradual fading of black holes might lead to fresh discoveries in physics, helping unite quantum mechanics, which rules the tiny scale, with gravity, which rules the massive scale. This merger is among the top goals of theoretical physics. Hawking radiation's relevance also extends to cosmology and the destiny of the cosmos. If black holes can eventually evaporate, it means the universe might someday be empty of them, leaving only the radiation they once gave off. That future universe would be very different, missing the massive bodies that helped shape cosmic history. Some ideas speculate that as black holes vanish, they might leave behind tiny remnants, Planck-scale particles, or unusual objects that could influence the universe's next phase. Even in the absence of direct measurement, Hawking radiation stands as a powerful theoretical tool that has changed our view of black holes, information, and the universe's laws. It represents where quantum physics, general relativity, and thermodynamics intersect, offering an exciting peek into the deep workings of the cosmos. As research pushes forward into black holes and spacetime, Hawking radiation will remain a core idea in our search to understand the universe's most profound secrets. Quantum superposition. Superposition. Consider the action of flipping a coin. In our large-scale world, the result will be either heads or tails. Yet in the quantum domain, particles reside in a superposition, a condition where they are essentially both heads and tails at once, at least up until observation. It's not merely that we lack knowledge of the result. The coin truly exists in several states all at once. This strange phenomenon goes against classical reasoning and puts into question our comprehension of reality. To comprehend superposition, one must first understand the probabilistic essence of the quantum realm. In classical mechanics, the movements of things are foreseeable if you know where they begin. Throw a ball upward, and its path can be predicted with accuracy. But in quantum mechanics, particles such as electrons or photons don't adhere to specific paths. Rather, they are governed by a wave function, a formula containing every possible condition the particle may occupy. When a particle is said to be in superposition, that means its wave function embodies several simultaneous states. One well-known illustration of this is Schrödinger's cat, a thought experiment. Here, a cat is enclosed in a box containing a poison that will release if a quantum particle inside undergoes decay. The particle's status, decayed or not, is dictated by quantum superposition, indicating it remains in both conditions until it's observed. Thus, The cat is regarded as alive and dead at once until someone checks. Though bizarre, this example highlights how superposition produces contradictions when it applies to larger scale objects. The idea of superposition was introduced in the early 1900s as scientists studied how particles behaved at atomic and even smaller levels. Experiments with light and electrons, like the double-slit test, showed effects that could only be clarified if particles also acted like waves. If individual electrons pass through two slits, they make a wave interference pattern on a screen. This behavior only makes sense if those electrons are in superposition, moving through both slits at the same time. Quantum superposition isn't purely theoretical. It has been proven in labs many times. In 2010, researchers at the University of California created a superposition using a very small object, one you could see without tools, a tiny metal paddle. Though this object wasn't as big as Schrödinger's imaginary cat, it showed that superposition doesn't just belong to the quantum micro world. It also hints at where the quantum and classical worlds intersect. But what occurs when we look at a superposition? This is among the strangest features of quantum mechanics. As the Copenhagen interpretation suggests, when we take a measurement, the wave function collapses. This collapse compels the particle to settle on a single state. Before being observed, a particle sits in a spread of probabilities. Observation restricts it to one outcome. That brings up deep questions. What exactly is an observation? Does it need a conscious observer? Or is any contact with the surroundings enough to make the wave function collapse? The link between superposition and observation is crucial in areas like quantum computing. In those systems, quantum bits, or qubits, can be in a superposition of both 0 and 1. This differs from classical bits, which are always one or the other. Because of this trait, quantum computers can carry out multiple computations all at once. This drastically boosts their capacity in certain fields. For example, using superposition, quantum algorithms can break down large numbers or explore databases much faster than standard methods. Superposition also has a part in quantum cryptography, where it offers unmatched safety in communications. In systems like quantum key distribution, information is encoded in superposed particle states. If anyone tries to intercept, it causes the superposition to collapse, making tampering obvious and maintaining secure data transfer. One especially interesting use of superposition lies in quantum biology. Some scientists argue that superposition plays a part in how photosynthesis works, or how birds navigate. In photosynthesis, it might allow energy to flow efficiently across light-absorbing molecules by traveling many routes at once. Likewise, some birds may rely on quantum features in their vision to sense the Earth's magnetic field and help guide their flight. However, superposition stirs as many puzzles as it answers. Why isn't it something we see in daily life? The explanation could be a concept known as decoherence. This happens when a quantum system touches its surroundings. The superposition states become tied to countless particles in the environment. That interaction washes away the superposition, making it unnoticeable in large-scale systems. This is why quantum effects usually stay hidden on bigger scales, and why Schrödinger's cat would, realistically, never be both alive and dead. The many worlds interpretation offers a different viewpoint. It claims that each possible result of a quantum event takes place in its own branching universe. In Schrödinger's setup, the cat ends up alive in one universe and dead in another. This explanation doesn't require collapsing the wave function, but it leads to a wild idea. an endless amount of parallel universes, each tied to a different quantum outcome. Superposition also touches on deeper questions about reality itself. Is the quantum world fundamentally based on probabilities, or does it hide a fixed structure we haven't uncovered yet? This discussion between randomness and determinism affects thoughts about free will, cause and effect, and the very basis of existence. Even in cosmology, superposition sheds light. The early universe likely existed in a superposition of quantum states, with its development shaped by quantum fluctuations. Those fluctuations left behind patterns in the cosmic microwave background, the radiation that reveals the universe's large-scale makeup. Understanding superposition here might offer insight into how the universe began and how spacetime works. The strange and non-intuitive nature of superposition forces us to stretch beyond what classical physics teaches. It pushes us to question assumptions, like whether objects have set properties, whether time always flows the same, or whether reality is separate from observation. By accepting the contradictions in superposition, we step closer to deeper truths about the universe. In the end, quantum superposition is more than a physics theory. It is a powerful signal of how intricate the universe is and how limited human awareness can be. It points to a realm where particles inhabit several states, where observing can define outcomes, and where certainty blends with possibility. This concept not only builds our understanding of quantum laws, but also fuels awe and investigation into the true nature of reality. Gravitational waves. Waves. You are by a calm pond, where the surface is still, reflecting the blue sky above. Suddenly, a stone hits the water, causing ripples to move outward, distorting the pond's smooth surface as they travel. Now, instead of a stone, imagine something vastly more massive, like two black holes colliding or a supernova exploding. And instead of a pond, picture the very fabric of space-time. The ripples caused by such cosmic events are known as gravitational waves. These waves are among the most astonishing yet deeply insightful predictions made by Albert Einstein's theory of general relativity. They present an entirely new approach to observing the universe. At its core, a gravitational wave is a ripple within the structure of space and time, triggered when massive objects accelerate and create distortions in space-time itself. These waves travel at light speed and deliver information about the universe's most energetic and violent phenomena. But for a long time, gravitational waves remained unobservable. They were just theoretical predictions, ideas that couldn't be proven for many years. It took nearly 100 years before scientists had the tools necessary for direct detection. When those waves were finally detected, the result wasn't just a scientific achievement. It was a transformative moment that revealed a brand new observational window into the universe. How did this happen? And why are these waves so exceptional? Let's begin by reviewing the theory behind them. According to general relativity, space and time aren't two separate things. Instead, they are a combined four-dimensional continuum called spacetime. Objects with mass, like stars, planets, and black holes, bend this spacetime around them, similar to how a heavy object on a rubber sheet causes it to curve. This bending is what we understand as gravity. In the case of gravitational waves, when massive bodies such as orbiting black holes move around one another, they disrupt the fabric of space-time, creating ripples that radiate outward. These ripples behave like the waves on a pond, oscillating as they pass through space, stretching and squeezing space-time as they go. When gravitational waves reach Earth, they can cause extremely small variations in the distances between objects. In theory, Even the most finely tuned instruments wouldn't detect them, unless those waves came from extremely energetic and violent cosmic events like black hole collisions or neutron star mergers. Einstein introduced the idea of gravitational waves in 1915 as part of general relativity. He realized that accelerating massive bodies, like two orbiting stars, wouldn't just curve space-time. They could also send wave-like disturbances through it. However, Einstein initially believed these waves would be far too weak to ever detect. For many decades, gravitational waves remained only an idea. That all changed in 2015 when scientists at the Laser Interferometer Gravitational Wave Observatory LIGO made an incredible announcement. Gravitational waves had been directly observed. These particular waves came from the merger of two black holes, located approximately 1.3 billion light-years away. LIGO's ultra-sensitive detectors picked up a clear signal, the sound of space-time being disturbed by one of the most catastrophic events known, the fusion of black holes. This historic detection confirmed one of general relativity's boldest predictions and gave birth to an entirely new field in astrophysics. What actually occurs during one of these events? When two black holes, or other extremely dense objects, begin orbiting each other, they send out ripples through space-time. As they spiral inward, these waves grow stronger, much like how pond waves increase when a stone sinks deeper into the water. Once the black holes finally merge, they release a tremendous burst of energy as gravitational waves. These waves carry crucial data: the black hole's masses, spins, and the nature of the collision. Yet, by the time these waves reach Earth, they are incredibly faint. Detecting them requires tools of unimaginable sensitivity. LIGO's detectors use laser interferometry, where a laser beam is split and directed along two perpendicular arms. When a gravitational wave passes through, it causes minute changes in the distances along these arms by stretching and compressing space-time. The difference in distance is tiny, about 1,000th the width of a proton, but it can still be detected with incredible accuracy. The 2015 detection lasted just a fraction of a second, yet within that brief moment, scientists gleaned a vast amount of information about the cosmic event. That discovery was both a scientific triumph and a powerful example of human brilliance, an achievement made possible by decades of hard work by thousands of engineers and scientists. Gravitational waves do more than reveal black holes. They also provide insight into the early universe. Their detection could help us uncover how the first stars and galaxies formed. By analyzing wave patterns, researchers can study extreme conditions, like the insides of neutron stars or the dynamics of black hole mergers. Why are gravitational waves so vital? It's because they offer information we simply cannot obtain otherwise. Light, whether it's visible, ultraviolet, or infrared, can be blocked or distorted by cosmic dust and gas, making some parts of the universe hard to observe. Gravitational waves, on the other hand, pass through all matter without obstruction. That's what makes them such a revolutionary astronomical tool. They allow us to observe the cosmos in a previously impossible way. The 2015 gravitational wave detection marked a new beginning in astronomy. Since that moment, LIGO and its European partner Virgo have captured several more significant events. This includes the detection of neutron star collisions, which also produce gravitational waves. Each discovery has offered a completely new outlook on the most violent occurrences in space, with many more yet to be uncovered. However, harnessing the power of gravitational waves comes with enormous challenges. The shifts in space-time they cause are extraordinarily small, and the tools needed to detect them are extremely fragile. LIGO, for instance, must identify shifts as tiny as 1,000th of a proton's diameter. That requires nearly perfect precision, as well as advanced systems that cancel out interference from things like ground vibrations, traffic, or even air molecules. Despite these difficulties, our capacity to detect gravitational waves has opened a bold new chapter in understanding the cosmos. It's provided a new lens through which we can witness the most intense cosmic occurrences, like black hole collisions or neutron star fusions. Each wave detection brings more knowledge about how gravity, space, and time truly operate. The discovery of gravitational waves is a vivid reminder that our universe is far more active, mysterious, and profound than we had imagined. It shows the strength of human curiosity, brilliance, and the never-ending quest for knowledge. And as we continue exploring these waves in space-time, we will certainly unveil new truths about the cosmos, truths that have been hidden from view for eons, only now being revealed by the waves of the universe itself.